Hello students, this recording is for topic 5 on chemical energetics, thermodynamics and thermochemistry. I think the last recording was done in 2021, which is based on the old syllabus, and of course that was my inaugural recording, and it was done in a relatively rushed manner. So all this while I wanted to do a re-recording, and just nice, the new syllabus is being introduced. So but just to take note that whether is it the new syllabus, meaning you guys JC1 taking exam in 2026, or whether you guys are in JC2 taking the exam in 2025, end of this year, right? There isn't much changes to the contents of energetics. So you can still use this recording, or if you wish to, you can use the previous one. But maybe before I move on with the recording, I just want to showcase to you where to find the information. So if you go to SEAB website, seab.gov.sg, you can try to find 2026 GCE A-level syllabus examine for school candidates. Make sure it's 2026. You guys JC1, so you will take exam next year. Okay, so if you scroll down, you need to go past H1, so you move on to over here, chemistry. So there is 9729. So 9729 is the old syllabus. So make sure that you don't click on this. So 9729 is for the current batch of JC2. Okay, for your batch, I think you need to look at this 9476. Okay, so the specimen paper is indicated here, paper 1, 2, 3, and 4. You can just click on it, and then you can take a look at the questions if you wish to. So again, for current batch of JC1 taking exam in 2026, your syllabus is 9476. For current batch of JC2 taking exam end of this year, your syllabus code is 9729. Is there a huge difference between the two syllabuses? Nope. Not much difference, except that for the current 9476 syllabus, there is a small topic being introduced, that is the polymer chemistry. Okay, so the recording will come later on, so please keep a lookout for it. Right, so now let's get back to the lecture proper. So again, as per all our lecture notes, the learning objective directly lifted from the syllabus document is presented for you here. So if you wish to know what the details are, you may go to this front page, the first 2 pages, and take a look at what exactly you are being tested on. Okay, so you can go through some of these things as you revised. So quite a bit of things for energetics. So the lectures in total will take quite a bit of time, but no worries, you'll be all recorded. Okay, right. Okay, so for introduction, most of you should be quite clear, right? Because you learned this before in secondary school. Okay, so basically the energy content in a substance is called the enthalpy. So in the course of a reaction, the energy is either being taken in from the surrounding or being given out to the surrounding. Okay, so based on what you learn in secondary school, if energy is being given out to the surrounding, what exactly is happening is that you experience a rise in temperature. So this rise in temperature, you can record it using your thermometer. So for such reaction, it's called exothermic reaction. And the energy content of the product is lower than that of the reactant. Why is that the case? Because energy is being given out, so the net energy content of the substance is lower than before. Okay. Are there any reactions exothermic that you are familiar with? Absolutely. You are familiar with a lot of exothermic reactions. For example, burning of a piece of paper, burning of the candle, right? Or even the dissolution of some salt. And then you experience a slight warm feeling or sensation on your beaker if you try to dissolve some salt in water. Okay. Then for endothermic reaction is not so common in nature. For endothermic reaction, the energy content of the product is higher than the reactant. So that means that for that to happen, the energy must be taken in or absorbed from the surrounding, and that leads to a drop in temperature of the surrounding. That means the surrounding feels colder. So for that to happen, the reaction mixture must absorb energy or heat, or energy in the form of heat from the surrounding. Okay, so that will result in the final product having a greater energy content as compared to the reactant. Yeah, so you'll notice that we use this particular term quite exclusively, heat, here. Okay, you might have seen a particular term in secondary school, even sometimes Cambridge exam at the secondary school level make that mistake. Heat energy. Okay, so take note that there is no such thing as heat energy. Yeah, heat is heat. So heat basically is a term used to describe the transfer of thermal energy from one body to another body. Yeah, so the transfer of thermal energy is in the form of heat. There is no such thing as heat energy. So be very clear about this. If not, you might end up as a laughing stock, when you go for interviews in the future. Right? Okay, so I'll move on to next. Then you're going to get something known as the energy profile diagram. So this is not really an energy profile diagram. This is called an energy level diagram. So maybe I can highlight this. This is an energy level diagram. So if you move on to the next page, they have something called the energy profile diagram. You would have seen this before in secondary school. Yep. So what is the difference between the two? For an energy profile diagram, it tells you in general how many steps the reaction undergoes. So for example, for table 2, right, these two reactions is a one-step reaction. Okay, so you have the reactant here, the products here, and then over here, there's a name attached to it. It is known as the transition state. Okay, how long does a transition state last? Many years ago, I think in the year 2000, Nobel Prize was awarded to Ahmad Zewail, who have since passed away, I think some years ago, for this area of studies known as femtochemistry. Okay, so transition state lasts around 10 to the power minus 15 seconds. So that is 1 femtoseconds. Yep. You cannot isolate transition states. Yeah. So in the older textbook, transition state is also known as activated complex. Yeah. But this particular term has since been discontinued. Although I think in some of the more traditional university, you would have seen this term as well, activated complex. Yeah. So the peak is known as transition states, and then before and after, reactant and product respectively. Okay, so every reaction definitely will have transition state. So the transition state will either be between the reactant and the product for a one-step reaction, or between the reactant and intermediates for a multi-step reaction, or between intermediates and intermediates. Yeah, we will go more into details when you study reaction kinetics as well as organic chemistry. But right now, at least at the H2 level, you will not be doing a lot on energy profile diagram. Okay, yep. Then another key difference between the two is that if you look at the energy level diagram, right, the transition state is not shown. Yeah, so basically the energy level diagram just show you the difference in energy between the reactant and the product. That's about it. Yeah, but for the energy profile diagram, you see the transition state being indicated as the peak. Okay, then again, the difference between the product and the reactant, okay, will tell you whether the reaction is endothermic or exothermic. Yeah, so I need you to be clear about this, right? And when you move on to university, this is no longer called progress of reaction. Okay, there is another term attached to it. Okay, but I will not discuss in details over here. So at least at the H2 level, it is okay to write it as progress of reaction. Okay, if you are interested, the other term is known as reaction coordinates. Okay, but I think this term seems to be a bit different from the meaning of the term progress of reaction, because progress of reaction is actually not so correct as well, because it seems to imply that there is a timestamp attached to it, like going from left to right. Yeah, but technically, in the course of a reaction, you can either go left to right or right to left. It doesn't really matter because the direction is not that important for an equilibrium reaction. Okay, but nonetheless, at least at the H2 level, progress of reaction is used. I think that is fine. Okay, so 1.4, you have thermochemical equation. So the definition, or rather the explanation is given here. A thermochemical equation is a balanced equation that includes enthalpy change of the reaction. Yeah, you do take note that state symbols is being written. Yeah, so for all thermochemical equations, the state symbols is mandatory because once the state symbol changed, the value changed. Yeah, so it is state symbol sensitive or state sensitive when you write out the enthalpy change. Okay, so there's an explanation given here. The equation indicates 285.9 kilojoules of heat released when 1 mole of hydrogen gas reacts with 0.5 moles to give this. So that's quite a mouthful. Yeah, sometimes for simplicity, at least at the H2 level, we try to understand the per mole by highlighting that this actually means we are looking at 1 unit of the reaction. Okay, so that means that this per mole don't really have a meaning if you are very strict about it. Yeah, so are we talking about per mole of hydrogen that gets oxidized by oxygen or per mole of water that is produced in the course of reaction? Yeah, so if it helps, you can just think of it as 1 unit of the reaction gives you releases 285.9 kilojoules of energy. Yeah, then if I use 2 units, 2H2O2 produce 2H2O, then the delta H will be double. Yeah, so to be fair, to be really fair, when you go to university, this per mole disappears because strictly speaking, it is incorrect to put a per mole there. Yeah, but for H2 wise, it tends to be quite common for Cambridge exam, and that's why we decide to include it as part of the learning process. Okay, so I hope while listening to the lecture, you don't get confused. Yeah, so there are just certain things that I guess we have to prepare you guys for exams. So in the process of preparing you guys for exams, there are certain things that we need to compromise. And along the way, as per all the earlier lectures or the later lectures, anything that is compromised will be highlighted and will be verbalized so that you can take note of them. We have an example here. I think in the past we don't write out the solution for you, but over here it's written for you. So maybe I can discuss it with you over here, although comments and solutions are given, but sometimes it might be easier to listen to someone talking. Okay, so you're asked to write out the enthalpy change of the reaction for the following reaction. Okay, you notice that this reaction is the reverse for this. Yeah, if you try to track the state symbols, it's the same. So liquid water, gaseous hydrogen, gaseous oxygen, half a mole. So if you reverse it, you change the sign. Yeah, as simple as that. Okay, so basically if a forward reaction is exo, the backward reaction will be endo. Yeah, how can we understand it? We can understand it from this graph if you want to be strict about it. For reactant, okay, so let me erase. When I go from reactant to product, if I give out heat, okay, so this is exothermic. Yeah, but if I reverse it from product, if you consider this as a reactant and this as a product, the reverse will be delta H, same magnitude but different sign. Yeah, so if you look at it from the energy level diagram, I think the logic can be easily seen. Okay. Yeah, so there's a comment there. If you wish to, you can read through. Yep. Then this is double 2H2 gas plus O2 2H2. I think I mentioned that before. So because I use double the amount of reactant, I produce double the amount of products, I will give off double the amount of heat. So strictly speaking, there shouldn't be a per mole here, but for the purpose of Cambridge exams, because they tend to highlight the students in writing out as per mole of equation, So 1 unit of this equation gives out 571.8 kilojoules of heat. Yeah, so therefore we want to teach you based on what you've seen in Cambridge exam, so therefore we include the units in as well. But strictly speaking, there shouldn't be units. So I hope you get the perspective where I'm coming from. Right. Then next, for part B, take note that the state symbols is a little bit different. Okay, so right now you have hydrogen gas react with half a mole of oxygen to give gaseous water, that is steam. Okay, so the value is negative 241.8 kilojoules of energy instead of 285.9 kilojoules of energy. Okay, so I'm going to show you from another perspective. You are probably going to learn it anyway later on, but I'm just going to write it out for you so that you can learn this fast. Okay, so I'm just going to write the two equations out side by side. Okay, hydrogen plus half O2 gas. I'm going to get liquid H2O. Okay, so this is negative 285.9 kilojoules. Okay, then for the other one, to get gaseous oxygen is negative 241.8. So I'm going to draw the arrow down sideways. So this is negative 241.8. I'm going to add H2O gas. Okay, right now, will you be able to see the difference? The equation on top gives you liquid water, but the equation below gives you gaseous water or steam. Okay, so what's the difference? The difference is that in order for you to transform from liquid to gas, you need to undergo what we call vaporization. So you need to absorb heat in order for vaporization to occur. Correct? Remember that if you want water to boil, you need to heat up the kettle, right? You know, plug in, put water into the kettle, and then plug into the socket, and then turn on the power supply, and then you'll hear heat being released, and then your water will slowly be raised itself to 90 degrees Celsius, and then 95, and then 100, it starts to boil, and then you stop, right? Yeah, so heat is required to be input when you want to boil water. Yeah, so that means that we're actually looking at the missing link, which is what I've written in red. So this, from H2O liquid to H2O gas, this delta H is actually positive. Okay, it's actually positive. Yep. So if you are able to add these two values up, this and this, you will be able to get negative 285.9. How do you do that? You take negative 241.8 and then you reverse the arrow, like you're solving it like vectors, and then you should be able to get negative 285.9. Okay, if this one sounds a bit too difficult, what I can do is you can actually find out delta H. Okay, what do you do to find out? You can reverse this arrow and then add this. So the delta H is essentially plus 285.9 minus 241.8. Okay, you can easily get plus 44.1 kilojoules per mole. If you understand everything that I've just explained to you, congratulations. You understand the basic of what we call the Hess cycle. Later on, we're going to introduce to you. Okay, if you don't understand so far, it's fine. Yeah. Of course, there's an explanation here. You need to convert liquid water to vapor. So 44.1 kilojoules of energy is required to be absorbed per mole of water, and therefore that explains why the value is lesser than expected. All this, yeah, I mean, this is just an explanation, the reasoning behind which I've just highlighted. Okay, but you can actually do the calculation if you wish to. Right. Okay, 1.5. These are all definitions. The use of the terms standard conditions. So standard condition at a specified temperature is the pure form at 1 bar. So 1 bar is 10 to the power of 5 Pascal. Remember this? Yeah. So the standard state of ethanol is a pure liquid ethanol, 298 Kelvin, 1 bar. Yeah. So the actual enthalpy cannot be measured, but you can arbitrarily set their standard state to 0 if you wish. Okay, then there is a little symbol you need to include here, delta H naught. So it's a difference in enthalpy in their standard states and the reactor in their standard states. Yeah, so good to know the definition here, because sometimes they will ask. Temperature is 298 Kelvin, pressure is 1 bar, concentration of a solution is 1.0 mole per dm cube. Okay, you need to highlight the reference temperature when you define standard enthalpy changed. Yeah, because it need not be 298 Kelvin. So usually it's 298 Kelvin because that is the temperature we are working with, and we are most comfortable with, but may not be always the case. Okay, so there's a little note here. The C solid here refers to the graphite allotropes. You might want to be aware of this. It's not diamond. Yeah, so the standard state of carbon is the graphite allotropes. So it has a lower energy content and is more stable than diamond. Oh, you'll be very surprised, right? So does that mean that all the diamond eventually will get converted to graphite? So of course the answer is no. Yeah, the reason being there's a missing link between the diamond and graphite that is not shown in the energy level diagram, but it is shown in the energy profile diagram, but I don't think the energy profile diagram is shown. Yeah, that is also what we call the kinetics of it. So the activation energy is very high. So it doesn't mean that an exothermic reaction will definitely occur. That is the most common misconception students have, that exothermic reaction confirm plus guarantee will take place. No, because there is still one layer, that is the activation barrier. Okay, so without any information of activation energy, it is difficult to conclude whether one reaction is preferred over the other. Okay. Okay, section 2. You have more definitions here. Again, students ask sometimes, do we need to memorize the definition, etc. That chemistry seems to have a little bit more memory work as compared to physics. Well, I mean, it really depends on perspective. I think physics has its fair share of definition as well. Yeah, but for energetics, it is important for you to know the definition for all the energy terms, for a very simple reason, because if you are not sure about the definition, you cannot solve the problems presented to you in our tutorials or in our exercises. Yeah, because most of the time at the H2 level, when the problems are presented to you, they are problems related to asking the students to draw a cycle or to interpret a cycle, or I think about 60-70% calculation based. So if your definition is shaky, you are not going to get the correct numbers out from I mean, you if you can't define it, you can't draw the cycle. As simple as that. So maybe you can, to the best of your ability, every day or every other day, try to remember 2 or 3 definitions. There aren't a lot. I think less than 15. Okay, Ken. So with that in mind, maybe we go through them one by one. I think we can do it quite fast, but I mean, since we are here. So 2.1, you need to understand what is enthalpy change of reaction. Basically, it's any reaction, okay, that is taking place under standard condition. Yeah, so like for example, ammonia and HCl react to give you ammonium chloride. So they give you the delta H to be this value. And then copper and silver plus undergo redox reaction to give you delta H of this value. Anyway, this is the standard enthalpy change of the particular reaction that we are talking about. Yeah, so nothing too fanciful, just take note that we're talking about reactions. Okay, as specified by whatever system you are being given. Okay, what is more important is probably enthalpy change of formation, because if I were to ask you a definition, I will ask you this. Yeah, so formation of what? Formation of the product of a substance. Okay, so 1 mole of that particular substance, any substance. It can be ammonium chloride, it can be silver chloride, it can be NO2, N2O, whatever you want, for its constituent element in their standard states. Okay, so this definition, very clear cut. I think you need to quote it word for word. So it's the formation of 1 mole of anything. In this case, for HI, will be 1 mole of HI. Yeah, from its constituent element, that is hydrogen and iodine, half a mole each. Standard states of each of them is gas for hydrogen, solid for iodine. Okay, so do take note of this definition. We tend to ask you once in a while. Yeah, so enthalpy change of formation elements in their standard state is of course 0. Yeah, because you are just quoting this again. So enthalpy change of formation of 1 mole chlorine is from constituent element of chlorine is chlorine, right? So it's 0. Okay. Yep. So this is just by linking up some of the facts you know. So if the enthalpy change of formation is positive, the compound is less stable than the constituent element. Yeah. So decomposition might take place, but it might not go to the constituent element. So they say likelihood is not a guarantee. It's not a must. Okay. Then if it's formation of positive, then product is more stable than the constituent element. Yeah. So less likely for decomposition to take place. Yeah. So just some simple inference. Okay, then this bullet point, enthalpy change of formation are often theoretical, so you cannot, you can't measure it, if you know what I'm trying to say. So that means that that there is no way for me to say I give you oxygen, I give you hydrogen, I give you carbon, and then you put them together, and then I'm going to get ethanol. No, most likely you're going to get CO2 and H2O. Yeah, so because enthalpy change of formation are theoretical, they are usually determined through the use of Hess law. Okay, so for exercise 2.1, supposed to write the enthalpy change of formation of calcium sulfate. Yeah, so normally I find it useful to leave a lot of space to my left. Just put an arrow here and then put calcium sulfate. State symbols is important. Okay, then I'm going to look at the constituent elements. So I have calcium, I have sulfur, I have oxygen. Okay, so what I'm going to do is I'm just going to write calcium first. So calcium will be solid, it's a metal, right? Then plus sulfur. Sulfur you can represent it with S or S8, but usually I like S8 because it's more correct. So that will be 1/8 S8. Okay, then how many oxygen do you have? You have 4 oxygen in total, but there is no O4. Okay, if there's no O4, what do we have? We have O2. So again, 2O2 gas. Yeah. If I'm going to remind you again, the state symbols is important, extremely important. Okay, so make sure that you have the state symbols in all your energetics equation or all your thermochemical equations. Okay. Standard enthalpy change of combustion. So it's a heat evolved. Combustion means evolved heat because you burn in excess oxygen, and this is important, completely burn in excess oxygen. Okay, so you burn and burn and burn, but make sure oxygen must always be in excess, because if oxygen is not in excess, the highest oxidation state of that particular element might not be reached. So for example, for the case of hydrocarbon, if you do not have complete combustion, you might end up with CO. Okay, I mean, in everyday life it's dangerous, right? But for the case of definition, you're not going to get accurate values, or you are probably not able to perform the calculation well because you don't know the proportion of CO and CO2, and it gets complicated. Yeah. So for the case of enthalpy change of combustion, you must always remember that it is completely burned in excess oxygen. I think just have that phrase in. You will always be safe. Okay. Then what about this? Okay, so this is interesting because it has 2 names. Really depends on the perspective. Okay, so the first name is the standard enthalpy change of formation of water. Standard enthalpy. Standard enthalpy change of formation of liquid water. Okay, or I can call it the standard enthalpy change of combustion of hydrogen gas. Yeah, so it depends on the perspective you want to take, and then you name them accordingly. Okay, yep. Okay, next we have the standard enthalpy change of neutralization. Okay, neutralization. Okay, so you might have seen this in your microbit practical 4, right? I think this term might be introduced to you by your tutors, so just maybe you can take note of it somewhere. Okay, there is link. Okay, this is the heat evolved when 1 mole of water is formed from the neutralization between an acid and a base 298 Kelvin 1 bar. Neutralization is exo because the formation of water largely is due to the formation of the HO bond between H plus and OH minus, the oxygen and OH minus. So this value is pretty standard, negative 57.0 kilojoules per mole. Yeah. Normally we are looking at strong base and strong acid. That means that the starting ground, right, is a complete ionization of the acids and the base. So we only have H plus and OH minus mixing with each other. No, you do not, the system does not require you to overcome any specific bonds. Yeah, so largely we are looking at only bond formation of HO. Yeah, so therefore in that condition, when you try to mix strong acid and strong base together, with the correct condition, of course, you are almost guaranteed to get, if you perform the experiments correctly, you are almost guaranteed to get the enthalpy change of neutralization value to be about negative 57.0 kilojoules per mole. Yeah. Okay. Yeah. So effectively, we are looking at this particular equation. If your tutors did explain to you in class. Okay. The rest of the spectator ions, they are not involved. But for weak acid, it's a different story, because for weak acids, they are partially ionized. Okay, so the heat being given out in the production of water, right, will be used to further ionize the weak acid. So in the case for ethanoic acid, the HO bond will be overcome by the heat being released in the formation of water. Yeah. So because of that, because bond breaking is endo, and bond forming is exo. Yeah. So the enthalpy change of neutralization between strong acid with weak base or weak acid with strong base will usually be less exothermic. Okay, yeah, so I think that might be something you need to be familiar with. Okay, so we're going to end of this section. Yeah, so in the next video, I'm going to discuss the experimental determination of enthalpy change, so keep a lookout for it.